Let's use the notion of angles in standard position from part 1 to actually extend the definition of the trigonometric functions. So we understand how to work with acute angles. So I'm going to start a little bit from what we know and work toward some new areas. Let's say we have some angle theta that's 30 degrees. So we can sketch what that looks like in standard position. We would get an angle that might look a little something like that. In this situation, to define the trigonometric functions, we can do the following. We can create a sketch like I just did. So I'm going to sketch the angle in standard position. And then I need to be able to identify, in order to find a function value without a calculator, I need to identify a point with x and y coordinates on the terminal side. So I need to be able to find some point with x and y coordinates on the terminal side of the angle. Once I have that point, I can draw a vertical line to the x-axis. This creates what's called a reference triangle. And with these sorts of problems, it can get a little confusing, but remember, you always want to draw a vertical line to the x-axis. And so that might come up from the terminal side, or it might come down from the terminal side, depending on what quadrant your terminal side is in. So that creates, to write it down here, that creates a reference triangle. That's the right triangle that we're going to use to define the trigonometric functions. So use this triangle to find trigonometric function values. Well, with 30 degrees, I can use a special right triangle, the notion of special right triangles, to find a point x, y. Most convenient, I know that the hypotenuse here, if this is 30 degrees, I know the hypotenuse has to be twice the opposite side, and then the adjacent side would be the square root of 3. So I can think of that vertical distance, the length of the vertical side, as being the y value, and I can think of the square root of 3 as being an x value, and I'll call the hypotenuse, because we're dealing with sort of a circular sort of motion around the origin, I'm going to label that with an r now instead of an h. I'll label it with an r to indicate that it represents a radius. So with those letters, with x, y, and r, we can define the trigonometric functions in the following way. Sine is y over r, because y now represents the opposite side. Cosine is x over r, and tangent is y over x. And we can see that for 30 degrees in particular, and for other acute angles in general, things like the cosine of 30 degrees work out to be what they should. They agree with our earlier definition. If I take the x distance, the x coordinate of any point on the terminal side, and divide by the value for r, I get the value that we would from just any old right triangle that has 30 degrees in one corner. I get the square root of 3 over 2 as the cosine value for 30 degrees. I should add a note here that r is equal to the square root of x squared plus y squared, using the Pythagorean theorem. What makes this notion kind of powerful, is that we can use it to extend to any angle. So suppose I want to figure out the sine of 150 degrees, and perhaps also the tangent of 150 degrees. Well, in a similar way, I can create a diagram of that angle. 150 degrees would look something like this. The terminal side is going to be in the second quadrant. And if I draw from any point along the terminal side, if I draw a line down to the x-axis, I create that reference triangle. What's called the reference angle in here, you might notice the reference angle would actually be a 30-degree angle, because to get all the way to the negative x-axis it would be 180 degrees. So with this diagram, I can choose any point along that terminal side, and it makes sense to choose one that's convenient. So I could choose again the value for r to be 2, and then the value for y is going to be 1. But now, because we're in the second quadrant, the x value should be negative, so I'm going to take the value of x to be the negative square root of 3. Which means that using this definition, we do get something a little bit different for 150 degrees than we saw for acute angles. Sine of 150 degrees doesn't seem too unusual. I get 1/2 the y value over the r value. But for tangent is y over x, and because we're in quadrant 2, that x value associated with this triangle, the x value is negative. So I get 1 over negative square root of 3. And so the new sort of thing, the newest aspect of this is that with an extension to angles of any size, we do end up with negative trigonometric function values. So a key idea here is that we need to know a point on the terminal side. And if I know that, then without a calculator, I can set up a reference triangle in a similar way and figure out trigonometric function values. A problem that really emphasizes that point is the following. Suppose we know the terminal side of angle theta passes through the point 2, negative 3. And what I'd like to do is find secant of theta and find secant of theta and tangent of theta. So this is a little bit different than our earlier problems because I don't know the value of theta, but I don't need to know the value of theta because I'm given a point. Right? So 2, negative 3 is on the terminal side. The x-coordinate of 2, the y-coordinate of negative 3 places us in quadrant 4. And from that point, I can build, as we did with the angle measures before, I can build drawing a vertical line to the x-axis. I can build a reference triangle. And from the coordinates of that point, 2, negative 3, I know that the x value that I'm going to use to define trigonometric functions is going to be 2, and the y value is going to be negative 3. And r, because r squared equals x squared plus y squared, I know that r equals the square root of x squared plus y squared. And so for this example, we get r equals the square root of 13, because squaring the negative 3 makes it positive. So the hypotenuse, the longest side here, r, is going to be the square root of 13. And then, as you might expect, secant is still going to be defined as the reciprocal of cosine. So secant of theta is r over x. And so we get the square root of 13 over 2. And tangent of theta equals y over x. And so we get negative 3 over 2. So in a later video, I'll give some additional examples, but let me end here with a statement of just kind of the general idea. So again, the general idea is that for any angle theta, I can create a sketch in standard position, and then if I choose some point, and it can really be any point along the terminal side, and draw a vertical line to the x-axis, that allows me to define a y-coordinate, an x-coordinate, and an r-coordinate. In quadrant 3, those are both going to be negative, but regardless of whether they're negative or positive, I can from that define sine of theta to be y over r. Cosine of theta is going to be x over r. Tangent of theta equals y over x. And the reciprocals are the same as they were before. Cosecant of theta is the reciprocal of sine. Secant of theta is the reciprocal of cosine. And cotangent of theta is the reciprocal of tangent. So with what you've seen in the video, take a few minutes, please. I encourage you to try to answer the following question. What would be the cosine of negative 210 degrees? And also, try to find the sine of 135 degrees. Thanks for watching.